Okay, today is a first for this channel. We're actually going to be doing some physics. So let's go ahead and explain the situation. We have a mass hanging or swinging from some sort of string, right? And the string is just twisting around, and the mass is making a circular arc in the plane. And then I went ahead, labeled some stuff. In a previous video, we did derive spherical coordinates, but these coordinates that I'm going to use here are a little bit different because phi is a little bit shifted from where it usually is, and it's shifted from where I derived it. So I went ahead, drew some relevant diagrams, and I hope that everyone can see where I got this for my position vector. So this is my position vector. I just said it's my relative position, and it doesn't really matter, where we measure from, because what really matters, where I'm going with this, is the velocity and acceleration. So the position doesn't matter much. The relative position doesn't really matter. So let's go ahead and find the velocity from the position. So that means taking the derivative with respect to time. First things first, this bottom is just a constant, and so when you differentiate it, you just get 0. So down here, we'll just put a 0. And that makes sense because the mass isn't moving up and down because it's going in an arc in the plane. Okay, next thing, these are constants. We can just factor that out now that this is 0. Also, we'll put a negative here because the derivative of cosine is negative sine. But then we have to put a negative here, so the derivative of sine is cosine, but we put a negative. Okay, and then you have to notice that you have to use a chain rule, so you have to multiply with the time derivative of theta dot. And what's theta? Is just some arbitrary angle. It's just some number that's supposed to quantify where in the circle the mass is. Okay, that's really what it is. It doesn't really have a place on this diagram. So what is theta dot? Well, theta dot is in fact, it's in fact the angular velocity, right? So we could write it as an omega, and for the purpose of this video, we'll assume that the mass has a constant angular velocity. Okay, so we'll assume it has a constant angular velocity. So we'll just call that W, and we'll move that out. Okay, this is cool. So now we are left with this. Sorry. So now we're going to go ahead, differentiate once again to find the acceleration vector. And here we go. So when you differentiate sine, you get cosine. When you differentiate cosine, you get negative sine. The negative and the negative cancel. And we do get sine theta. And then, and then again 0. It's just going to end up being 0 down here. Okay. And then we still have our stuff up here. Cosine phi. So now we have an extra theta dot from these derivatives, so we can go ahead and just call it omega squared. Okay, there it is. So we've derived the velocity and the acceleration. So now let's go ahead. We have these formulas. Let's see what they actually mean in context of our problem. First things first, notice how similar these guys are. So just take a look at this. We see we have a p cosine phi in common. And actually, this is our r. If you look, let's see, if we do cosine of phi, that will be this. So actually, yeah, this right here can be replaced with r. So we do get that v is negative r theta dot, and then a is negative r theta dot, and then squared. That's fine. Or, I'm sorry, these are magnitudes now, not the actual vectors. So the magnitudes are like that. And this is very strange. And you don't actually need these minus signs for magnitude, since you're going to take the absolute value. But take a look at this. You can sort of express a as v squared, right? But then divided by r. Right? So our magnitude of our acceleration is the velocity squared over r. And this is a very nice formula in physics, and it helps you solve a lot of circular motion problems. So now we solved for the magnitude of acceleration, and we got this nice formula. But what about the direction, right? So I will go ahead and first draw the velocity. So here we see we have our position as this sort of vector right here. And our velocity is actually sine, cosine. It's actually exactly tangent. So let's say it's here. Our velocity vector would be exactly tangent to the circle. I suppose I could draw better. So our position would look like that. Our velocity would look like that. So how would our acceleration look? And I guess I'll just draw a picture down here for just to be a little bit more clear. So this is our velocity. So what would our acceleration need to be so our mass keeps on moving in a circle? Well, this is gonna look like this. So it's gonna be pointing inwards towards the circle. And this is our centripetal force. This is the force that the string is exerting on our mass. And you can tell by looking at the formulas notice how the acceleration is cosine theta sine theta, but it's actually negative. So it's exactly the position, but negative, and the z term isn't there. So it's pointing towards the center of the circle, or just like that. And there we go. Circular motion.